So today we are looking at the operator's code. For a long time, many have viewed the blast furnace as a black box, unpredictable and mysterious. But the reality is that the furnace stability is never random. Every physical zone of this machine, this vessel, or we can say this reactor, is governed by a strict mathematical balance. Today we are going to master the five core formula that drive heat, pressure, and descent matrix. By understanding this relationship, we move just watching the gazes, from just watching the gazes or observing the data to actually controlling the furnace pulse. Now, this guide is your operational reference to ensure that every shift is predictable, safe, and productive also. So, let's break down the code. Now, a map of the five critical zones and their governing balances is being shown in the slide. So, as you can see on your right hand side, the three factors, and on your left side, two factors. The right side, if you see the charging, the second one is on the belly and stack basically, and on the third basically on the cohesive zone. And similarly, on the left hand side, if you see this tuyere and hearth becomes the two segments, the critical zones we can say, where our basically focus will be. So in totality, we can say these physical five zones are our focus area. So before we dive into maths, so let's look at these all five components. So we have, as you can show that this all divided into five, and we have already pronounced each of it. And once again, we want to recapitulate, like the top cone for the charging, the stack for the burn and descent, the cohesive zone for the gas flow, two-air breast for the melting, and the hearth for the slag chemistry. So notice that each zone has its own unique formula. If the furnace slows down, you should not just guess what's wrong. You should look at which zone is out of balance. Are we charging too slowly for our production? Is the upward gas pressure beating the weight of our burden? Is our slag basicity too high? Over the next few minutes, we will look at each of these five zones individually. So we will exactly find out or locate which lever to pull and when things to drift. So now coming to the ability to use the charging rate as a real-time production indicator. Our first formula is for the top charging zone, that is basically the production here roughly uh, equals the charges per hour. The principle is simple. The material we put the top is only there because the material at the bottom has been processed. So coke is consumed at the tuyere and the ore layers melt into iron and slag. So to keep the furnace stable, we need a steady burden descent, which requires regular charging and a stable stock line. So your key indicator here is the balance between your casting rate and your charging rate. If iron is leaving the taffle faster than you are charging at the top, you will lose your stock line. So remember, your charges per hour are your most direct real-time window into your true production rate. And this is the very true statement that each operator has to aid in memory. Now coming to the stack, so understanding that body weight must always beat upward pressure. So in this zone 2, the stack, we manage the physics of descent. The the formula is the downward force of the burden must exceed the upward force of the blast pressure plus hearth liquid. Now, this is a constant tug of war. Naturally, the pressure gradient resists the descending burden. If the upward force temporarily wean, the burden stop moving, and this is the hang. And this is the stage which is to be avoided by each operators. So when those forces finally give way, the burden drops rapidly, but there is a huge cost of this dropping in terms of rushing off red coke from the uptake, damage, even a lot of red coke rushes to our dust catcher, creating a lot of refractory damages. So, as an operator, your diagnostic clue is simple. If the furnace is hanging, check your liquid level. If the tap hole is closed and the hearth is full, that liquid creates massive upward resistance. Empty the hearth to relieve the pressure and get the burden moving again. And that we have to catch hold at a right time. So if you take a longer time, then magnitude of the after effect will be higher, our losses will be higher. Coming to the cohesive zone resistance time, as you can see that identifying, particularly in this zone, identification of the fines is the primary threat to the gas permeability. And we must have to catch hold of these fines, threat of fines. Otherwise, it will kill our permeability. And once the cohesive zone is affected with this permeability, that becomes a bigger effect. The magnitude of the effect, bad effect, is much bigger. So the cohesive zone is where the ore begins to soften and melt, and if this zone affect, then our damages control will be very high. So the formula here is the resistance of ore, which is 4 times higher than the resistance of coke, because the melting ore is so dense, it creates a immense resistance to upward gas flow, as it's a well-known principle, and all operators know. So to keep the furnace breathing, we charge ore in thick ring with a coke chimney in the center to act as a highway for the gas. So your biggest threat is this zone is having if a lot of fines, any material smaller than 5 millimeter, then these peony particles fill the gaps between our larger particles and effectively kill our permeability. So when gas cannot get through the center, it's forced to the wall and leading to heat loss and instability and carrying a lot of heat to the wall, where the cooling system drain these heat losses without getting utilized in melting or reducing the iron ore. So to keep the fines out, to keep the gas flowing, should be our objective for this zone, and this helps in meeting a consistent productivity. Now coming to controlling the flame temperature as the engine of melting, we can see this zone 4 is the tuyere raceway, the engine room of the furnace. The formula for heat availability is gas volume multiplied by the difference between the flame temperature and the melting temperature. So we blast preheated the air into the furnace to generate a flame between 2000 to 2300 degrees Celsius. As an operator, your levers are oxygen enrichment, fuel injection, and moisture control. So these are what you use to keep that flame temperature in sweet spot. So be alert for the hard stop. If that flame goes dull at the peep side, it often means a water leak has extinguished the heat, or passive or inferior material, carbon-based material. So if our some peeling, so many reasons may exist. So if the flame stops, the entire melting process stops. So keep your lances centered and your moisture level stable. Now maintaining a B3 basicity below 1.5 hard limit to prevent the freezing. So finally we reach the hearth. Here we manage the B3 basicity index, which is the ratio of lime and magnesia to silica. This index is critical because it determines the temperature at which our slag turns to liquid. Our goal is to keep the slag highly fluid even at the lower temperature, so it flows easily through the furnace and the runners. We have a hard limit we must memorize. B3 must never exceed 1.5. If it does, the slag will solidify almost instantly, potentially freezing the hearth. So if you see your index climbing towards 1.5, you must act immediately by charging extra coke and a low basicity burden to thin that slag out before it stops flowing. So now coming to our next slide, which is on basically a operator's pocket guide. Here, uh, to wrap up, we have the operator's pocket guide as it's shown in the slide. And this is basically a diagnostic matrix. So this brings all five formula together. When the furnace talk to you through the symptom, you now have the code to translate it. Now, if you see stock line hanging, you know to check your hearth liquids to relieve the upward pressure. If you see the top pressure or the poor gas flow, you know the cohesive zone is struggling with the fines. If the flame is dull, check for the water leak at the tuyers. And if the slag solidify in the runner, your B3 index is too high and need an immediate shift in burden chemistry. So use this five formula as your map and you will always know the right move to make the production safer and